thank you, Ethan, for giving me the host. Since it's not quite time, I'll wait for like a minute or two, or I'll wait until 4 o'clock to get started. So, yeah. Um, okay. So just a quick reminder, Zoom for some reason doesn't let me look at the Q&A during the class. So if you have any questions, just put it in panelists and I can see all your questions in panelists. So yeah, okay. I'll wait for another minute or two before we get started. And if you don't see something, or if like you don't see my typing, or if you don't see anything, just like let me know. Yeah. Okay, so let's get started. So, hey guys, my name is Rushil, and today, we're going to be discussing some physics, and specifically, we're going to be talking about dimensional analysis and error propagation. And the special thing about these two topics is that they are rarely discussed in like physics classes in schools or even outside, but they still appear on the F equals MA exam. And since not many people talk about it, I would like to like discuss it in today's class so that you guys will have a common understanding. And also, dimensional analysis is a powerful tool used by many physicists, graduate physicists throughout the whole entire world to solve complex problems. And it gives like an estimate of a range of values that an answer could lie in. So these both of these topics will also help you later in life. Okay, so let's get started. And we'll begin by recapping what we did last week. So in last week, we discussed energy and work. And work is given as the formula work is equal to the force on an object times the distance the object moves while there is a force on it. So if we have some object here and we apply some force, F, for a certain distance, D, then we will apply a work, F times D. And then we also talked about energy. So we talked about the types of energy, like kinetic energy, which is related to the motion of the object, the potential energy, and it's two types: gravitational potential energy, which is the potential energy caused by the gravitational force, and the spring potential energy, which is caused by the spring force. And we also talked about conservation of energy. And this just says that energy is always conserved. It's neither it's only converted or transformed into different types of energy. It's never created or destroyed. So, and we use this conservation of energy to solve problems, like when we want to find how much let's say some object is traveling and it like collides with the spring, causing the spring to compress. And conservation of energy will allow us to find the distance that the spring would compress. Okay. And lastly, we talked about power. And power is the energy over the time, or work over time. And we related power to force. Okay. So let's begin with today's class. And today, let's start off with dimensional analysis. So let's discuss what dimensional analysis is. And this is just the analysis of using the units of different variables to find an equation for a new variable. So basically what this is like you have the units, so you have a bunch of different variables like velocity, acceleration, force. So all of these have different units, like velocity has meters per second, and then mass has kilograms. Acceleration has meters per second squared, like that. So we use the meters per second squared, and we try to combine those units to get a final unit that is some other value. So like, let's say we're trying to find how acceleration and mass create force. So we look at the units of acceleration and mass, and we somehow try to combine them in such a way that it creates the units for force. And that allows us to create an equation for force. So that's basically what dimensional analysis is. We use the units of different variables, and we do that, and then we are able to find an equation for a new variable. Okay, so does anyone have any questions on what dimensional analysis is? Okay, so if there's no questions, I'll let you guys try a simple problem showing dimensional analysis. And most of you guys probably already know this equation, but just try doing it using dimensional analysis. So look at the units for each of the velocity, displacement, and time, and see how you can rearrange the units of displacement and time to make it equal to the units of velocity. So try example 1, and I'll give you guys like 2 or 3 minutes to try. Okay, so I see a few good answers. Keep them coming. Okay, so try finding the velocity in terms of displacement and time. Don't use acceleration or any other variables, just displacement and time. We'll go over the other variables a bit later. Okay, so let's try this problem. So when we write the units for something, we don't write kilograms or meters or seconds or anything. We use different letters. So we use L for length, T for time, and M for the mass, or M for the mass of the object. So length can be like meters, feet, miles, time can be seconds, minutes, hours, or and the mass can be kilograms. So instead of writing like kg or something for the mass, we do M instead. So using these three these three letters, let's try writing the units for each variable. So the units for velocity, well, we know that the velocity is meters per second, and meters is L. So we have L and per second, so over seconds, and seconds is time. So the units for velocity is length over time. And the units for time is just t, and the units for displacement, which is just the distance, which is a length, is L. So we want to rearrange, like we want to somehow make t the time and L the displacement into L over t. And the way we do this is by doing the displacement, which is L, over the time, which is t. And that gives us units of L over t, which is the velocity. So this means that the velocity v is going to be our displacement d over our time t. Because the units of displacement is L and the units of time is t. And this is the same as the units of velocity. So therefore we know this equation is correct. Okay, so does anyone have any questions about this example? Okay, so if there's no questions, let's continue. And here is a chart that I made, and this has a bunch of common physics quantities, physics variables like displacement, time, energy, momentum, and their units in terms of L, T, and M. So if you guys want, you guys can like jot this down or take a screenshot or something and when you need to use it, you can use it later. So I'll give you guys like a minute or so to just copy this down, minute or two to copy this down. And any of the equations or any of the stuff that you find here that you don't that I didn't write the units for, you can probably derive them by some other equation. So for example, density. So density is represented by this rho. So density is the mass of an object over its volume. And the mass of an object has units m, and the volume of an object has units L cubed. Because remember, like if you're trying to find the volume of a square or something, you cube the side length. So that's like cubing a distance L. You're cubing a distance. So this will have in the denominator L cubed. So using this formula, you are able to find the units for the density, which is m over L cubed. So if you don't know how to find, if you don't know a certain unit, you can always derive it using some formulas. Okay, so just let me know if you're still copying this down, and if not, if no one's copying it down anymore, if everyone is done, then I'll move on. Okay, so it seems like everyone is done copying it down. So we'll try to do some practice problems that will help strengthen our dimensional analysis skills. So I want everyone to try example 2. And I'll give you guys like a few minutes to try. So remember, if you want to use dimensional analysis, first you have to find the units of each variable. And then once you find the units of each variable, you have to try combining them to find how, if you combine them, how are you able to get the units of the last variable? So in this case, we want to combine the units of length and acceleration to get the units of a period. remember that you don't need to just multiply and divide. You can also like take the square root, you can square them and things like that. Okay, so to help you guys out, I'll give you guys the units for each of these variables. So the units for period can be seen up here. So we have time and period, and that has units of t. So the period will have units of t. Okay, and then the length will have units of, well, the length is just a distance. So the length is going to have units of L. And the gravitational acceleration, well, this is the acceleration. So if we have acceleration here, so this means it's going to have units of L over t squared. Okay, so now we have the units for each of these quantities. And we want to somehow find t in terms of L and L over t squared. So we want to rearrange L and L over t squared so that we get t. So try figuring out how can we rearrange them so that we get t. And remember, once you find the equation using L and L over t squared, make sure to plug back in the variables. So if we have L, instead of putting L, put this L. And instead of putting L over t squared, put G. So plug these values, your variables back in. Okay. So, okay, so let's try solving this together. So we want to get t by somehow manipulating L, and manipulating L over t squared. So in our final result t, there is no L. The L's got canceled out. So this means that if we do L over t squared divided by L, like this, or opposite, or if we flip this around, the L's will cancel out. So this leaves us with 1 over t squared. So now we want to convert this 1 over t squared into t. And remember, we can if we take the square root of this, the square gets canceled, taken out. So let us take the square root of this quantity. And by taking the square root, this square will get taken out. And we're left with 1 over t. And finally, to get the 1 over t to t, we can take the inverse. So we do 1 divided by this. Or this just means we can just like flip the numerator and denominator of the fraction inside our square root. So this is just the same thing as L over T squared. And you can verify that if we simplify this out, the square root of L over T squared, this will give us T. So let me quickly show. So first, these L's will cancel out because both of them are in the numerator. And this leaves us with, so let me just draw an arrow. This leaves us with the square root of 1 over T squared. Or 1 over T squared, my bad. So 1 over T squared. And since we're finding the inverse of the inverse, this just get canceled out. So we're just left with the square root of T squared. And this is just T. So this means that in terms of the units, it's L over T squared. And now all we have to do is plug back in the length and the gravitational acceleration. So L is for length in the numerator, so we have this L in the numerator, and we have L over T squared in the denominator, and that's G, gravitational acceleration. So we have G in the denominator. And this is our formula for the period. So right here. Okay, so does anyone have any questions? Okay, so if there's no questions, then I'll move on. And one thing that's important is that this might not be equal to square root of L over G. This might have some factor of like 2 or maybe 3 or some other dimensionless constant. So if there's a constant that doesn't have any dimensions, like a number or something, then this can still be in the front. So this might not be the correct equation, but it's very close. And in reality, if you were to find the period of a pendulum, which you can do by looking at Newton's laws, and it's a bit more complicated, but if you do that, there's actually a factor of 2 pi in the front. So just by using dimensional analysis, we were able to find the period of the pendulum, or at least up to some constant. We were able to find the period of a pendulum without even knowing any physics. We just needed to know the units of each thing, and we were able to find the period. So that's one way dimensional analysis is pretty cool, because it allows us to find certain equations that we wouldn't have been able to do if we didn't know the concepts. Okay, so I'll let you guys try example 3, and I'll give you guys a bit more time this time because this is a bit more tricky problem. And in fact, this is from our recent F equals MA contest. So I'll let you guys try this out. Remember to first find the units of each variable, and then you can find the equation. Okay, so let's just quickly find the units of each of the variables, and then I'll let you guys um, continue solving this problem. So we have the drag force, and we're given that it depends on the length of the fish. So the length, its velocity, and the density of water. So we have F is equal to, which is our force, is equal to some combination of R, V, and rho. So the units of force is going to be the mass times the length over time squared. The units of R, which is length, is just going to be L. The units for V, which is velocity, is going to be length over time. And the unit for density, which we derived earlier, if we go back, so density has units of mass over L cubed. So rho will have mass over m cubed. M over L cubed. Okay, and now that we found the units of each of these quantities, we have to figure out how can we combine R, V, and rho in such a way that their units equal the units of F. So find a way to combine L over T, and M over L cubed so that it gives us ML over T squared. So I'll give you guys a few more minutes to try the problem, and then I'll explain. Okay, so let's try and see how we can combine these different quantities to get us ML over T squared. So we see that this F, this has an M, and the only quantity here that has an M is rho. So we know that there must be a rho somewhere. And it can only be to the power of 1 because the M is to the power of 1, and on the other side, the force, M has a power of 1. So far we have M over L cubed. Now, let's look at some other quantity. Let's look at T. So we see that there's a T squared in the denominator for the force. And in these equations, the only one that has a T is the velocity. So we want to put the velocity in the equation in such a way that we get T squared in the denominator and the final answer. So velocity already has T in the denominator. So by squaring velocity, so if we do V squared over here, so we multiply this by the ln squared over the time squared. And we see that we get our T squared in the denominator. So we have our M and our T squared. And we can get rid of, so there's an L cubed in the denominator and L squared in the numerator. And we can just cancel this, and we're just left with an L in the denominator. Now we want to move this L from the denominator to the numerator. And we can do this by multiplying by L squared. So by multiplying by L squared, we get rid of this in the denominator and the second power is gone. So we're just left with ml over t squared. And the L squared comes from R squared because R has units of L. So by squaring R, we get L squared. And you can quickly verify that if we plug in the units, we get that this is equal to the force, units of force. So our force will be equal to the R squared, V squared times rho. Okay, so now let's look at what the problem is asking. We want to find how fast a clownfish, 1 centimeter in length, needs to swim so that it experiences the same drag force as the pufferfish. So the force F on both of the fishes is going to be the same. And this means that R squared, so R1 squared times the V1 squared times rho. Well, the rho is the same for both objects because the density of water will stay constant. So R1 squared times V1 squared, this will be equal to the R2 squared times V2 squared, or the radius and velocity squared of the clownfish will be equal to the radius and velocity squared of the pufferfish. And all we have to do now is plug in the values of R and V for each of the fish. So if we let R, or if we let V be the velocity of the clownfish, then we get that 10 squared, which is the radius of the pufferfish, times 5 squared, which is the velocity of the pufferfish. This will be equal to 1 squared, which is the radius of the clownfish, times the clownfish's velocity squared. And now we just have to solve this for V. And if we solve for V, we get that V is equal to 50 meters per second. So our answer will be 50 meters per second. Okay. So does anyone have any questions? Okay, so since there's no questions, I'll move on. And remember, if you have any confusion, don't be afraid to ask. Just send your question to panelists and I'll be sure to answer it. So don't be afraid to ask any questions if you have any. So moving on, let's go to our other topic we'll be discussing today. And that topic is error propagation. But before we talk about this, we need to find some key terminology or some key vocabulary. So the first important vocabulary we need to learn is uncertainty. And uncertainty is an estimation of how much a value of some quantity deviates or is different from its observed value. So we use this delta or the other delta to signify an uncertainty. And basically, what does this mean? This means that let's say we have some object and we want to measure the mass of the object. So we put it down on some instrument to measure the mass. And the instrument tells us some value. The instrument isn't perfect, right? It's going to give us it's not going to give us the exact value because the exact value is very, very hard to determine because of, for everyday life. It makes there might be some friction, air resistance, something that causes the measurement to be inaccurate. And this causes there to be an uncertainty because when you read the measurement, you're not 100% sure that the measurement is exact. Like it might be off by some amount. So that amount that we think the measurement is off from the real value, that's the uncertainty. Okay, so now let's take a look at error propagation and what this is. So error propagation is the study of how uncertainty will affect the final value. So error propagation is like when we take a bunch of measurements and we combine them and we try to find the final uncertainty. And this is a really important tool for all type of scientists and mathematicians because when they do some experiment, it allows them to find how strong their data fits the expected data. So for example, if we take measurements of some mass, like some number of times, and we add them together, we want to find the uncertainty of our final value or something like that. So the F equals ma tests how we can the uncertainty of something when we add some objects or we multiply them. So here are some rules about uncertainty that are tested in the F equals ma competition. The first rule is addition. So whenever you want to add or subtract some variables that have some uncertainty, remember we denote uncertainty using this value. So or this Greek thing. So whenever we draw this is a delta. So whenever we draw this means uncertainty. So if we're trying to add some variables that have uncertainty together, our final variable will have some uncertainty. So like if we have three masses and each one has an uncertainty, when we add those masses together, the final one will also have some uncertainty. So this is the rule that allows us to find what that uncertainty is. So let's say A is the uncertainty that we're trying to find. So the uncertainty of the final mass of the things that are being added together is the square root of the sum of the squares of the variable of the uncertainty of the variables. So for example, if like the uncertainty of the variables was like 0.1, 0.1, 0.1, you would just plug in 0.1, 0.1, 0.1, square them, take the square root, and then we get our final uncertainty. So that's the formula we use when we want to find the error of some quantity that's calculated when we sum or subtract some values with an error. Okay, so does anyone have any questions so far? Okay, so if there's no questions, let's continue. So the second formula is multiplication of errors. So when we want to multiply two quantities that have some error and we want to find the final error, this is the equation we use. So we have delta, this is basically the same exact equation except instead of using just delta A or delta B, we do delta B over B. Like, so we find the uncertainty over the actual value observed. So for example, if like there was a mass of 10 kilograms and there's an uncertainty of 0.1 kilograms, we would do 0.1 over 10, like that. So, and this is called a relative uncertainty, but that's not really that important. And yeah, it's basically just the same formula, except we just divide by the value that we observe. And the last rule that's tested, or like, it's not really tested. You can do it without, you can like solve the questions without using the last rule, but it makes it easier. But this rule requires calculus. So I won't talk about it in this class, but I'll just quickly explain the rule for those of you that are interested. So let's say that the f is some function of x. So let's say like we have f of x equals x squared or something like that. So if we plug in some x with some uncertainty, we get some value out of x squared. And we want to find the uncertainty when we plug in some value of x with some uncertainty. We want to find the final value. And in this case, the uncertainty is given as delta f is equal to f prime of x times delta x. And f prime of x is the derivative of f of x. So if you don't know what that is, that's fine. It's calculus. But in this case, what we would do is you would take the derivative of f of x with respect to x, so you would get 2x in this case. And this will be multiplied by delta x to find our relative uncertainty of x, of f, of our final value. Okay. So are there any questions before we do some practice problems? Okay, so it looks like there's no questions, so I'll move on. So yeah, let's do some practice using uncertainties. So everyone try example 4. And remember that a ruler has a length of 1 foot. So this ruler has a length of 1 foot. So as a hint, try figuring out how many times we need to use the ruler. And then we just have to add the uncertainties or add the values. So we have to use the addition rule for the uncertainties to find the uncertainty in his measurement. So try it out. You might need to use a calculator for this one if you want to find the exact value. But if you can leave it as a square root if you want. Or you could just round it to like 2 decimal places or something, whichever one you feel comfortable with. Okay, I'll give you guys 1 more minute to try the problem and then I'll explain. Okay, so let's try the problem. So we have Bob measures the length of his car, and he finds out that this car has a length of 2 feet. And we see that he uses a ruler. And remember, a ruler is a length of 1 foot. So when he measures his car of length 2 feet, he's going to do two measurements of the ruler. And each time he uses the ruler, he has an uncertainty of 0.5 inches. So every measurement he makes, he has an uncertainty of 0.5 inches. And he will be doing um, the two measurements with the same uncertainty of 0.5 inches. So um, the two uncertainties, so we're just going to use the sum of the uncertainties rule because he's making two measurements and we want to find the sum of the uncertainties of the two measurements. So this will be square root, and the sum of the first uncertainty is 0.5 squared, and then plus the second uncertainty, which is the same thing, 0.5 squared. And if we plug this into a calculator or we just like do it by hand, we get that this is equal to square root 2 over 2, which is about 0.71. So this is approximately 0.71. So our uncertainty would be 0.71 inches. Okay, does anyone have any questions? Okay, so if there's no questions, we'll move on to another problem. And this is pretty much the same as example 4, except it's not really a word problem. It's more of a just, yeah. It's basically just the same problem, except worded a bit differently. You still use the same formula. And I'll give you guys around 2 or 3 minutes to try. Remember to find the sum of the measurements as well. And that's pretty straightforward. Because the sum of the measurements is just going to be the sum of 1 plus 2 plus 3 plus 4. Okay, so let's try this problem. We have 4 measurements of 1, 2, 3, and 4. So these are the values of the measurements. And these have uncertainties of 0.1, 0.2, 0.3, and 0.4. And we want to find the sum of the measurements and the uncertainty of the sum of the measurements. So the sum of the numbers is just 10. So that's the sum of our measurements. And the uncertainty is going to be, it'll just use the same formula. So we use delta x is equal to the square root of the sum of the squares of the uncertainties. So we do square root of 0.1 squared plus 0.2 squared and so on. And when we add them and take the square root, we get 0.548, approximately 0.548. So the uncertainty in the sum of our measurements is 0.548. Okay, so let's try one last problem. This one is a bit more difficult, but it's essentially the same thing. And this problem came from the F equals MA 2020 exam, the A exam, and this is problem 23. And this time you're going to have to use the multiplication formula for uncertainties. So I'll let you guys try this and I'll give you guys again a few minutes for, in this case, probably more, like 4 or 5 minutes to try. And for those of you who forgot, but the equation for the spring force in terms of K and delta X, which is just a change in length, is F equals K, spring constant, times delta X. And in this case, delta X is not an uncertainty. So don't get mixed up with that. It just means the change in length. Okay, I'll give you guys like 2 more minutes and then we'll go over the problem. Okay, so let's go over this problem. We have Steve determines a spring constant K of a spring by applying a force F to it and measuring the change in length delta X. And so this is the equation for the spring force. So if he wanted to find K, he would have to divide the force that he applies and by the change in length he finds. So that's how he's going to find the spring constant, by dividing his force over his change in length. And the tools that he used have a constant absolute uncertainty. So F and delta X have a constant absolute uncertainty. And the important thing that this means is that delta F, so the uncertainty in F, is going to be some constant. So it's not going to change. This is going to be some constant C. And same thing for delta X. So this is also going to be some constant. And since both of these are uncertainties, he's obviously going to get the same. He's going to get an uncertainty in the spring constant. So he's going to get an uncertainty delta Ks in his spring constant value. Now, Tiffany wants to measure the same spring with the same tools, but she uses a force that's 5 times larger. So she's going to apply a force 5F on the spring. And we want to find her uncertainty in K. So her uncertainty in the spring constant in terms of delta Ks. Okay, so when Tiffany uses a force that's 5 times as large, the spring is going to stretch 5 times as far. So the new delta X is going to be 5 times the original amount. And now let's see the relationship between delta Ks and delta F and delta X. So we know that the rule of multiplication and division tells us that delta Ks, or I'll just write delta K for short, is over K. This will be equal to the square root of delta F over F. So delta F over F, this thing squared. Oh, is it just me, or can you guys not hear me? Because okay, so if you can't hear me, just leave and rejoin. Okay, so yeah, so this is the equation for multiplication. I'm just writing it out. So we have delta F over F squared, and the other one is going to be delta X over X squared. So this is the equation we get for the uncertainty in delta K. So when we apply a force 5 times as large and it stretches 5 times as far, we're now going to have 5F in the denominator and 5X in the denominator. So the denominators are going to get multiplied by 5. And in order for this equation to hold, this means that the denominator of this side must also get multiplied by 5. So we multiply this denominator by 5. But since the spring constant still stays the same, this means that her uncertainty will change. And since we're dividing by 5, or like the there's a 5 in the denominator, her new uncertainty will be the original one, which is delta Ks over 5, in order for the denominator to stay 5. So her uncertainty in K will be 0.2 times delta Ks. So the higher force that you use, the less uncertainty you will have. Pretty interesting. Okay, so does anyone have any questions? Yes, this is the last class. Okay, so if there's no questions, I guess, okay, so here's some further reading. There aren't really any good resources for these topics, but there are a few. So these are just two links of, one is a dimensional analysis handout link, and another is an error analysis link. And also past EFMA problems, Olympiad problems, those are great resources for um, problems to solve for these types of topics. And here is a survey for that you guys should fill out. So let me just quickly type this in the chat, and you guys can go fill that out on your own time. So .org/student survey. Okay, so just go ahead and fill that out. And yeah, that's it for today's class and the whole session. Thank you guys for joining my class. Hopefully you enjoyed or at least learned something. And yeah, so um, yeah, have a good summer, guys. And since the other panelist isn't here, we'll wait for him to come, and then I'll give him the host. And yeah, okay, so bye. Oh, and also, if you have any questions, make sure to put it on the Kid Teach Kid website.